from 4 grams of hydrogen. 4 grams of hydrogen is cheap. You can get that basically for free, right? Because it's in water, for example, right? Water has hydrogen in it. Do some electrolysis, get yourself some hydrogen gas, boom, you got some serious coin, right? Make sense? Okay, so now we see, oh, wait a minute. We started the conversation with your incorrect chemistry understanding, but that's the atomic mass. It is not, okay? It's approximately the atomic mass, but actually when we're doing the physics, it's really important that we understand that it's not exactly 4, and that little difference has a huge effect. So we'll use that number differently. Green maybe, contrasting with the fuchsia, that makes sense. Color scheme, awesome, as usual, okay? So I'm going to scratch the atomic mass, and instead, we're going to call this the nucleon number. Nucleon number. Okay? It's the nucleon number, meaning we're going to count up the nucleons. Well, what the frickin' frack is a nucleon? You have not really been familiar with that word before, but you're familiar with things that are in the nucleus and that are ons. So nucleon is really a portmanteau. I don't know if you guys know what that is. The word that's stuck together from 2 things. Like the nucleus consists of protons and neutrons, so we'll call those things together nucleons. We take part of this word, part of that word, stick it together, that's a portmanteau. You never stop learning. Okay, so nucleons are the number of protons and the number of neutrons together. Okay, so helium has in its nucleus 2 protons, 2 neutrons, insgesamt, that's 4 nucleons. Okay, 4 nucleons, therefore the nucleon number is 4. That is good? Good. Now, and in that context, obviously, we also need to reevaluate somewhat this number, because you guys generally think of this as the that's kind of true. And it's okay. We're going to kind of call it a little bit different. We're going to call it the charge number. Okay? The charge number. And the reason we're going to call it the charge number is because we want to expand this kind of notation. Whoa, I misspelled nucleon after just defining it. That was pretty lame. And I don't want to write nucleon number anyway. I want to write down charge number. Sorry, charge number. Okay, so this is the charge number because we want to expand the notation to other things, such as electrons. Okay? So, let's take a look at what we have so far. We have about 13 minutes, and we can still do some more stuff. And I'm not sure we're going to get everything done today, so we might have to finish Thursday. We're still doing the quiz on Friday, and Miles is getting nervous about that. Right? It is what it is. Monday, Tuesday off. I just don't think we can push it to the next Thursday. It's too far away. So I think we're just...
Tuesday off also?
What's that? Monday and Tuesday are both off. Yes.
Just one real quick question for you. The quiz on Friday, is it just modern or is it modern plus thin films?
It's modern, thin films, and diffraction.
Okay.
Yeah, everything that hasn't been covered yet, everything that has not been tested yet will be tested Friday. That is diffraction, thin films, and modern physics. Tillman.
Homework questions also on Thursday?
We gotta do it, man. We gotta do it. Okay, good. So, let's take a quick picture and then erase. And then let's do as much as we can today.
Where like it would bounce off and it would go through. And then it would go back again and it would it bounces off in a certain medium.
Gamers who have a picture in the back of their head for like 2 minutes.
Oh, that's not gonna take you that long.
30 seconds.
What section does this fall under? Like, is it just modern? Or is
This
it
is nuclear physics. Sehr gute Frage. Yes. So this is nuclear physics.
Oh my god.
That's my GL.
Graham Walford sucks.
That's hurtful, but I'm not gonna let that bring me down. I'm a strong individual. And so this is more empowers me. Good for you.
I mean, TV. $10,000 TVs.
Okay.
It definitely was a cheap one. I was expecting like a Mac turned around.
Okay. So,
I'm looking for front page.
yeah,
I have a question about electrons.
go.
If they're all spread out, how can a photon hit them if they're like everywhere?
Dude.
Yeah. So it's kind of like, I think a good way of thinking about it is that electrons are just like light in that they have wave and particle properties. And I think you're right. In order, especially when you think about it as a photon, right? A light particle, that light particle should hit a mass particle called an electron. So in that interaction, it's absorbing that photon. I would think of the electron as a particle that is transitioning. But as it's transitioning, it's popping from one wave state into another. Okay, so it might be going from the 1s orbital into the 2s orbital. I'm using this as kind of remembering that, okay, well that's like so many percent of the electron or probability or whatever we call it. The wave function changes by absorbing the photon. So yeah, that's kind of hurting your head, and it should, because it's weird.
So does it have like a center, the electron that the photon hits? Because then wouldn't it be like...
That's a really good question. I don't know the answer to that in terms of where does it have to hit in order for this to work. Okay, I'm not sure how how they need to interact in order for this to work. The center of the electron is of course in the nucleus, the 1s orbital centered on the actual hydrogen proton, but it doesn't have to hit the proton. That's not going to be right. Okay, so we've got a couple ways we need to take this. First of all, we just saw that we were able to put mass particles together and get a result that has less mass. Okay? And we can put this together in this little statement that if we have fusion, putting together of particles of so when you take light atoms and you stick them together, such as hydrogen and hydrogen makes helium, okay? Helium and helium and helium makes carbon, okay? That you can put these light things together, the result is always something lighter, therefore in that reaction there's a release of energy, okay? And that's not based on magic or something like that, but there's actually a table, right? You can look up the different precise mass numbers, the precise masses of the individual isotopes. And that will always be true, generally true of any reaction. Don't want to generalize too much. In general, lighter things, stick them together, you get something out that's, as a sum, lighter, less massive than the reactants, therefore there's a release of energy. Yes?
Is that also attributed to like bonding?
Yeah, you can look at it in different ways in this case. When you say bonding,
Yeah.
I'm assuming in your head you're thinking about electron bonding.
Yeah, intramolecular, yeah, like covalent bonds.
That is something completely different. So when we're talking about bonding in this situation, we're talking about how tightly the nucleus is bound. So this is a different type of binding energy than the binding energy that you're used to. So in chemistry, you're studying relatively small energies on the order of electron volts that have to do with one atom binding to another atom because of the interaction of the electrons. Here we're talking about the nucleons being glued together through the strong nuclear force. Okay, and as they attract each other with a strong nuclear force, and they're glued together, the force transmitters are by the way called gluons, which is cool. There is an energy associated with that, which is similar to the binding energy that's associated, for example, with an oxygen and an oxygen binding together to make O2, but those energies are very low. These binding energies are in the order of mega electron volts. So they're a million times bigger than those atom binding energies. Okay, and that's why when we release this energy, we can get so much energy out. So fusion of light mass nuclei releases energy, and then on the other hand, you also know that if you take heavy nuclei, they can actually release energy in a fission process. You've heard of this, yeah? If you have a nuclear plant that's using uranium, or an atomic bomb that uses uranium or plutonium, those reactions can then release energy when those heavy elements break apart to make lighter things, okay? So on the other end of the spectrum is that fission of heavy, again, mass nuclei releases energy. So, those are the two ends of the process. So, couple of important aspects here. This means, of course, there needs to be a fulcrum in the center. So everything that's light fuses and releases energy. Everything that's heavy can fission and release energy. That means there needs to be some point where it neither by fission or fusion will produce energy. Does it make sense? Yes?
And what's the difference between fission and fusion?
Okay, so fission is like breaking apart, like a fissure would be a word, and fusing and sticking together.
And that's
So
what we
fusion.
do as the science, yeah.
That's the actual word. Fission is breaking apart, fissioning, yeah? And fusing, putting together, would be making bigger. Okay? I was assuming that you guys have heard of it. Sorry.
Does using like a mass accelerator count as fusion? Like if you're
No,
throwing
that's
electrons
actually,
at-
that's more, it's better to think about it as similar to pair production. So if you use a particle accelerator, you give normally a proton and an antiproton, large speeds, and you're basically letting them run against each other like this, and eventually you whack them together. And because they have such large energies in this process, the energies can create other particles that are much more massive than the actual proton and antiproton are. Okay, very similar to pair production, only in this case, the energy carriers are the massive particles, the proton and the antiproton. Okay, so the kind of the fulcrum between the two is iron. Okay, and then iron is on the edge. It does neither. Right? Grammatically correct. Iron releases energy neither by fusion nor by fission. Sorry, there we go. Nor by fission. So iron is the limit. When I said light is defined as basically lighter than iron. And heavy is heavier than iron. So iron is the Kipppunkt, the one that basically tells you things that are lighter than that could theoretically fusion and release energy. Things that are heavier than iron could theoretically fission and release energy. That was the first point that's important at this point. Second point that's important is they release energy. So hydrogen fusing into helium from a chemistry perspective would be called what kind of reaction? Hydrogen fusing into helium would be called what kind of reaction? Okay, I'll help you out. It starts with exo and ends with thermic. Exothermic. It releases energy. Now, at the same time, uranium fissioning would be also exothermic. Okay? So, you can put this in word. Fusing hydrogen and fissioning uranium are both exothermic. But the key point being, those are exothermic reactions. The question I have, are endothermic reactions verboten or impossible? Yes, Killian?
No, I mean, if like you want to form uranium, I guess then it would take energy so it can release it
Sure.
and break stuff.
Exactly. So the other way around, right? If you wanted to fission helium, right, into hydrogen, or fusing, let's say, lead, which could be one of the end products of fissioning, ooh, dude, uranium's missing here, are still allowed, okay? Fusing lead are endothermic, and this is the key. That can still happen if you put in energy,
Yeah.
okay? If energy is put in, okay? Good. This is as far as we've gotten. Try to do the best you can with Modern 3. The third homework is assigned. We will use at least the first period Thursday to wrap things up, then kind of review / answer homework questions, and then Friday is the quiz that's going to bring the course to a conclusion, and then we're going to have a couple days for AP prep after Labor Day. Okay? Asked on mine? Dr. Howard?
I'm sorry, could you explain that, like, that last part of the parentheses?
Sure. So, generally, like, students will say things like, you can't fission helium. It's not allowed. Like, no, you are. Just because it's energetically not preferred doesn't mean you're not allowed to do it. It can happen. You just have to put energy in. In the same way with the iron, like iron's at the bottom. Like, you can't fission iron. Sure, you can fission iron. You just have to put energy into the process to break it apart. You can also fuse iron, right? Otherwise, you wouldn't have heavy metals. So everything that I don't know where any jewelry, but a gold is heavier than iron. Where the heck does it come from? The universe starts, hydrogen and helium, right? Supernovae generate heavy metals, such as gold and other things, through a fusion process that's endothermic of those heavy particles iron, fusing them into heavier things, which is part of the reason supernovae are so catastrophic. Because it's a huge energy sink that totally disrupts the star. Because not only are the reactions in the core no longer supporting it against collapse, they're actually sucking energy out of the system and accelerating the collapse. And within a few seconds, supernova.
Who's recording it? Who's recording physics?
Serious?
Oh, should we stop it?
Yeah, we should stop it. Stop it.